Hey everybody, good morning. This is Chris Mullins with Powermetrix. You may notice the room a little bit different. We had to move because we had an audit. And unfortunately, you may realize that this is not John Jones, so I do apologize beforehand. He actually had to go down and visit a customer. The COVID restrictions breaking down has been kind of good because we're actually able to get back and see customers. So I know John was excited heading down to southern Alabama to see some of our guys down there. I want to thank everybody for joining us. We've got a great special guest today. His name is Nick Candler. He's with GEC Durham. Great guy. And I'm kind of nerding out because he kind of gifted me a 0.15S CT. So I am super excited about it. It's the most accurate CT you can buy. It's on the market. Extended range, 0.15S, and I've been testing it, and I love the CT. So time pending, we're going to see if I can do a demo at the end of this presentation. But I know we want to kind of get to let Nick kind of advise us all about instrument transformers. One of my favorite topics too, by the way. So today we're going to talk about, again, instrument transformers with our buddy Nick. Next week, just a reminder, we will not be here. We're going to take a spring break, but we'll be back shortly the week after. So today we're going to introduce Nick. Again, he's with Durham Company. He's a regional sales manager. He's been employed with the Durham Company for 5 years, and he's taught multiple schools. He's taught at Glim's, he's taught in North Carolina. Some interesting facts, he's an avid hunter and an archer. And he currently spends his free time building a log home on his family farm in the Ozarks. You wouldn't want that. Oh, another fact, he's married of 15 years and has 4 kids, all under the age of 12. Godspeed, Nick. So at this point, I'll go ahead and turn it over to Nick. Nick, you ready?
Yeah, we're ready to go.
Awesome.
It's all yours, Nick.
Thanks, Jarrett. Thanks, Chris. Thank you, Powermetrix, for the opportunity and the kind introduction. So let's jump right into this in the interest of time, and we want to get to that high accuracy CT demo here at the end. So you have joined a presentation on low voltage instrument transformers, the who, why, what, where, when, and how of low voltage instrument transformers, not to be confused with distribution transformers, medium voltage transformers, medium voltage instrument transformers. We're talking about 600 volt class revenue metering instrument transformers. So these are made in the USA in New Bedford, Massachusetts. If I don't sound like I'm from Boston, I'm not. So I'm joining you here in the Ozarks. So again, thanks for joining along. Let's take a look at who uses low voltage instrument transformers. We're going to find these in the industry, uses those a lot. Solar, we see a lot of customers reaching out for solar. Down on the low end, these instrument transformers, the high accuracy tend to pick up a lot better. So the solar farms and solar installations use a lot of those. Restaurants are going to use these. We have a Chinese restaurant here in town that has a 1600 amp transformer on it, trans socket with instrument transformers in it. I've received some orders for tanning salons. So they crank the heat up in there and use substantial load. So farming operations, you'll see a couple products later in the video that show the need for farming operations using instrument transformers. Shopping malls, shopping centers, your Costco's and Sam's Clubs and Safeway, a lot of grocery stores use them. Theme parks, you're going to see use these instrument transformers in theme parks, and even some large homes are going to use these instrument transformers. My predecessor, Greg Tyree, told me that an acquaintance of his was responsible for setting up the metering at Bill Gates' home, said he had a 2400 amp service. So yeah, there's some big houses out there that are going to need some instrument transformers. But what are low voltage instrument transformers literally? So these are going to be a steel core. There's a couple different material types for that. The silicon magnetic core steel is historically what the industry used, but migrating to more extended range and some high accuracy transformers are using a paper thin nanocrystalline material for that core. So that's going to be your secondary windings and terminals along with an insulated product. A lot of manufacturers out there will use a rubber encapsulation. The GEC Durham uses a two-part epoxy. We'll see some benefits to that epoxy later, but that's essentially the materials of an instrument transformer. There are a few types of transformers you want to consider. There's a miniature bar type. There's a miniature window type. You've seen a lot of these before, I'm sure. You've done many installations. There's a medium bar type transformer. And then there's also a medium window type transformer. And the context and the application is what's really driving this. So there's a Padmount AP style of transformer. These are your large oval transformers that will go on those Padmount spades, Padmount transformers, or these will also go around your busing in a secondary connection cabinet. So we'll see one of those later. Large window type ADs and your large window type ACLs. These are the 5 prominent types of instrument transformers that your utilities are going to make use of. So what are the accuracy classes? There's more or less 3 numbers that we deal with, but there are multiple, I guess you could say, types of accuracy classes. We kind of bunch these into 4 main categories. So you have a standard, you have an extended range transformer, you have a high accuracy extended range transformer. These are 0.15 accurate. And then there's also a high accuracy extended range 0.15S transformer. So the ANSI guidelines for the test points of these are all different, and they're able to perform better at different levels. Obviously, there's a different cost for each of these, but we're going to look into a little bit of these as we go. But just want you to keep in mind there's a 0.3 accuracy range and a 0.15 accuracy range.
Real quick, Nick, go back.
Yeah, go ahead.
On that previous slide you were talking about, I wanted everyone to kind of see the big difference between the standard and extended range. Notice that on the standard CT, we can go all the way down to 10% of nameplate value and hold the manufacturer's specs, but with extended range, we can go all the way down to 5%. Big deal.
Yeah, and I want to make a correction there. That's 4%. The ANSI standard for extended range transformers is actually a 4%, so that's a typo on my part. But,
excellent. Thank you.
Yeah, good point. No, those are all important to highlight.
Yeah, this is why I was so excited about this particular CT, was because of I've never been able to go down below 10% and get a good reading. So super excited about it. But those who have kind of hung around for the presentations we had in the past, we do talk a lot about the benefits of the CT itself. Sometimes we'll talk about the accuracy class and that rating factor. And I know Nick will kind of talk a little bit about in the presentation about rating factor, why that's important, because rating factor can affect your accuracy as the temperature increases. So while we're waiting for Nick to come back, we'll switch over to the on-site demo. So kind of what I wanted to show was, this is the CT that Nick sent me. It's a 0.15S, that's the accuracy class he was talking about, extended range. And if you remember seeing on that chart, he said that can go all the way down to 4% of nameplate, all the way to the rating factor. So what he sent me was a 605 CT with a rating factor of 3. And the information I'm getting is all from on this nameplate here on the side of the CT itself. And they also stamp the nameplate value on the side so you can easily see it when you've got inventory on the shelf. You can grab it, see it, or you can see it when it's in the either cabinet or when it's mounted on the pole. But this is a rating factor of 3, which means that if you think about it, basically it's a 605 CT, so at 100% of nameplate, you've got 600 amps. And then if you have a rating factor of 3, you multiply that number times 3. So 600 times 3, 1800 amps is the max current you can hit the CT before it saturates. So it's kind of like this bell curve. So the accuracy kind of maintains, and then, but as soon as you hit over 1800 amps, the accuracy goes way down because you go into saturation. So using the PowerMaster 7 series, you can actually buy an accessory called the CT load boost cable. And this is the accessory cable we have here. So if you're looking at the CT, so you've got the primary line coming in here. So if you see the dot, I'm coming in through the dot side, and I've got actually 2 loops of this cord going through this transformer. So I'm going to drive the inside of the core of the CT and excite it and get it up to a certain amount. And so I can wrap this 2, 3, 4 times, as many times as I want. I can get through the window of the CT, and this is a large window, so I've got a lot of the ability to wrap it. So I'm going to wrap it 2 times.
Hey, Nick, can you hear us?
And then,
No, I just didn't hear us, Nick was in a pause moment, so
okay. And then so I've got the primary side here, then I got the secondary output here. So I'm going to drive primary, but I'm going to measure the secondary output of the transform here, the X1, X2 connections as it comes in. So Jared, if we can switch over to the PowerMaster now. So I've got this set up, and I'm going to, I have this PowerMaster, I could drive up to 50 amps one wrap. So let's say, for example, I wrapped it 4 turns, I can go up to 200 amps. But I really want to kind of focus on the lower end, which is where I really think is where the extended range CT shines. So I'm going to drive 15 amps, adding about 0.1 burden, and then with 2 turns. So 15 times 2 is 30. So the CT is going to see 30 amps as I drive it. I've got the CT already in my database, and I've already got the manufacturer's serial number. So let's go ahead and start the test. So it goes through the process of actually starting to drive the load. You may hear the fan kick on as it kind of ramps up current. And it stabilizes.
And while that test is running and stabilizing, I'm going to mute the microphones for just a second, check in with Nick. I think he's back, so we're going to see how that works. 1 second, people. Okay, we're back. Chris, go ahead.
All right, so the low box is stabilized, and I'm going to go ahead and press Start Test to test the CT. So that test came out pretty darn perfect. So again, this is a 0.15 SCT. That means at 100% rate of load, you're guaranteed, I'm sorry, within the range of the CT, you're guaranteed 0.15%. I am measuring a 0.02%. Fantastic. I'm not sure you can ask anything else for more. So this is what I'm driving. I drove 30 amps, and then I measure about a 1/4 amp on the secondary side. So that's right about 30 amps is right about what, 5% of the CT itself. So I was telling Nick this. I'm very curious what happens if I drop it below the 5% range. How does it look? So let's go back and let's drop this down to 10 amps. And that'd be 20 amps going down there. So I'm below the 5% range now, right? So when we hit start, so it's stabilized to make sure we get exactly 20 amps going to that transformer. Ready to test. .01% at below its manufacturer spec. So Nick, you got a fantastic CT here. That's all I got to say. So I'll turn it back over to Nick now.
Awesome. Thanks, guys, and my apologies for the technical glitch there. Had some issues transitioning back and forth between full screen and my presentation. So I'll do my best not to bore you, but with that said, again, thanks for the attaboys on the accuracy for that. And just to be clear, the ANSI guidelines for high accuracy transformers require that manufacturers provide a test report at 5%. So anything below that is just, I guess you could say, for free. So anyway, let's move on through our presentation. One of the whys of instrument transformers is for safety reasons. Obviously, whenever you can reduce the voltage down to much safer levels from 277, 480 down to 120 or 208, you're going to keep a lot of your utility workers and metermen much more safer. Insulation is another reason why that we use instrument transformers. There's an insulated barrier between the line and the secondary side whenever we convert the primary current into an electrical signal and then pick it up as a magnetic signal, and then pick that up on the 20 amp socket. So there's some insulation there. That's going to be valuable, obviously, for safety reasons, but as well for cost on the high-end metering equipment. So some of those high-end meters are pretty expensive, and by using instrument transformers, you do get a degree of insulation there. Economy is a big reason why. You're familiar with 100 amp, 200 amp, and 320 amp sockets, and every time you take a jump up in size, you end up with a much larger metering enclosure. So to do that for large services, it would drive manufacturing costs. It's going to drive shipping, storage, use valuable customer space. But I did provide a few pictures here just to give us a scope of that scale. Here's your 100 amp meter socket. They've been making these since Moby Dick was a minnow. It's been a long time. We're going to compare this one to our comedian friend Kevin Hart, just a little guy. 200 amp socket. This is your run-of-the-mill residential socket. This one you're seeing actually has 2 load side connectors, but that's your average guy next door. And then let's take a look at a 320 amp. You notice we're going from smaller to middle size and then a much larger enclosure. We're going to compare that one to our famous buddy there, The Rock. So yeah, if going big isn't best, we've got to go much smaller. And we use instrument transformers to do that. We're going to reduce the current down to 20 amps or less. And in some uses, utilities will use the voltage transformers as well to get down the voltage down to 120, 208. And we use a 20 amp socket to do that. So much smaller. If cost and space were primary factors, which one would you choose? We have a 600 amp service. We could have an NBA sized meter socket on the side of the utility. Wouldn't be very good for a pole mounted application either. But if we were to bring in a little 20 amp, yeah, much less costly and obviously much smaller. And yes, Kevin Hart is much taller. But anyway, where are the instrument transformers installed? Let's take a look at where we put these. Obviously on utility poles. You can see a couple instrument transformers dangling from the primary conductor here. This is kind of an old way of doing it. Necessity is the mother of invention, and so there are mounting apparatuses that manufacturers make that can account much better installation for those. Little trivia fact here, some of the earliest instrument transformers were color-coded as well. This was long before the advent of bucket trucks, okay? So when they would look up the pole, they could see a certain color. They knew which ratio that they were looking at, what they were dealing with. Just a neat little fact. Padmount transformers, okay, instrument transformers are popularly put in those. There's a Padmount transformer with some oval type transformers along with some voltage transformers. CT cabinets are a real popular option. A lot of utilities who share the ownership of that commercial installation will choose a CT cabinet. Maybe the customer owns the CT cabinet and the utility owns the current transformers. This would be an option in that context. VT sockets. A lot of folks don't know about these, but manufacturers make those to account for any voltage transformers. Maybe the utility will own the 20 amp socket and the voltage transformers, while the customer would own the CT enclosure, maybe in a separate location or something. But
Interesting.
tran sockets are a popular option these days. As a manufacturer, we're seeing more and more utilities switch over to these. 200 amp, 400 amp, 600 amp. There's a lot of different types, styles, mountings of the 20 amp socket in the door, but these are going to include both your current transformers and a lot of times your voltage transformers as well. So,
Nick, I'm assuming those tran sockets are mostly meant for saving space at the customer site.
it is, yeah, good question. Space is an issue, but we see a lot of utilities are doing this for convenience. Obviously, in the industry, the last 5 to 8 years, we've lost a lot of what we call legacy linemen, folks who had that tribal knowledge to build all this stuff out. And it's much more convenient if they've outsourced the installation of this stuff to the customer for a contractor to swing by the utility, grab one of these off the shelf, then the utility will come out and install the meter later or, energize it. So there's some convenience factors there.
Makes
and
sense.
also, you see those pole mount installations, the secondary wiring is really exposed. This puts it in a cabinet that keeps it much safer from the elements. So yeah, good question. Padmount is an option as well. This is a secondary connection cabinet with some integral busing, dovetail lay-in caps, and some large Padmount style instrument transformers. So, mentioned earlier, farming operations are a popular location for these. Generator transfer switches are used a lot up in the Dakotas and the upper Midwest, where you've got you need to dry corn or whatever you need to do up there. You can't afford to have an outage. Instrument transformers are used. So when do we use low voltage instrument transformers? Self-contained meter sockets can handle up to about 320 amps. Those are going to be the bulk of your residential homes. But anytime you get above 400 amps, that is when you're going to need to put in some instrument rated services. So old A-base and K-base enclosures tried to account for that, but we're seeing more and more that industry move away from those type of metering devices. So yeah,
Correct.
400 amps or greater, commercial, some industry, and some larger homes. The reason I say some industry is because at a certain point, a lot of the utilities will offer a primary metering rate, if you will, and they'll negotiate with the end customer to put in a primary metering cabinet, and those are going to include medium voltage instrument transformers. But anyway, so yeah, industry, and then again, the large homes are going to need some instrument transformers. Are there any questions to this point?
None so far in the chat area, no.
Okay, good. Let's dive into a little bit of the theory of how instrument transformers work. So there's going to be an AC signal that passes through the primary conductor. And when that happens, there's a related AC signal that appears on the secondary or the output winding. Now that signal is going to be a ratio or a proportion to the primary amps that are going in. So the meter is going to pick up that reduced signal and transmit it through the meter. It's important here to talk about the ratio of transformation. There's a couple terms that we use to describe what's going on here. We have a current ratio, or we refer to that as the nameplate ratio. This is a 200 to 5 amps, for example. We also have a turns ratio. In this case, 200 divided by 5 would be 40. And coincidentally, that's going to include 40 turns of copper wire on that current transformer. So 40 is going to be your meter multiplier, as some call it. Some refer to it as the billing multiplier. But that's the number that the utility uses to make sure that you get charged the right amount. If they were not to use that, then there would be some lost revenue there for sure. So anyway, if you use any voltage transformers, you need to multiply your billing multiplier from the CTs by that ratio as well to get your overall billing multiplier. Lots of billing multiplier errors happen across the country each year, and a lot of folks will bring in people with test equipment like Powermetrix, and they'll do a lot of testing and find out what's going on with these. And a lot of times they're able to solve some problems and save some money at the same time. So how do we choose low voltage instrument transformers? We need to take a look at the type of transformer that we need. We want to look at the load. We want to look at the rating factor. We need to consider burden, accuracy class, and then also we want to choose our current transformers by cost as well. So we're going to see those on the pole. You might choose a different transformer for the pole than you would a CT cabinet or a trans socket, something different. An oval style will be for your pad mount transformers. And then a secondary connection cabinet. You can use some of those large AD or ACL types in the secondary connection cabinet. But let's just be clear, though, a CT is a CT. So if you're in a pinch and you've got a current transformer with a hole in the middle, you can essentially use it at least in the short term for whatever you need it for. We want to talk about the load as well. The customer's usage is a huge factor. We want to consider the maximum demand of the user. We want to choose a transformer ratio that covers the entire load, and that includes the rating factor. So we want to make sure that we size by the rating factor and not necessarily the nameplate. Historically, a lot of folks thought, well, we've got an 800 amp service. We need an 800 amp or an 800 to 5 transformer. Well, that's not actually the best way to go about it. But if the ratio is too small, the transformer will not generate revenue on maximum loads. The CT reaches what we call saturation. It's beyond its ability to perform and register at the meter. But if the ratio is too large, the transformer may not generate enough revenue down on the lower end. So this is especially true for solar installations. And for standard accuracy transformers, our goal is to stay in that ideal accuracy range. That would be 3/10 accuracy for both standard and extended range transformers.
Nick, for solar rated sites that are instrument transformer rated, do you recommend a higher accuracy class than the 0.3s?
Yeah, good question. That comes up quite a bit. Yeah, unequivocally, yes. As you saw on that transformer, the parallelogram is a much tighter confines, and the manufacturers forced into a much more accurate transformer, and they do go in most cases way down on the low end as well. So it's I wouldn't say it's the holy grail, but in some sense you do get to have your cake and eat it too with a high accuracy transformer.
Gotcha.
So back to thermal rating factor. This is a feature of CTs that allows you to extend that range of that CT by up to a meter multiplier of 4, all within your accuracy class. In this case, 3/10 accurate for standard and extended range transformers. Little trivia fact: it was Duke Power Company and Associated Engineering developed the first 400% 600 volt class transformer at a ratio of 400 to 5. So additional core steel to reduce iron losses, and by adding more copper to secondary wiring to reduce resistance. So yeah. Thermal rating factors. We refer to it casually as rating factor, but it is actually thermal rating factor. established temperatures are 30 degrees, 55 degrees, and 85 degrees. And so when a current transformer is placed in an environment that it exceeds its ability to perform, at some temperature level, the performance is going to be reduced, and it will reach saturation.
Nick,
Keep in mind, though.
hey, Nick, dumb question.
Yeah, go ahead.
I got a dumb question for you. So let's say, for example, I'm a utility down in Florida. No, let's say I'm a utility down in Arizona, and I've got a pad mount instrument transformer. Would it be better for me to have a pole mount, because I'm not going to have to worry about the high temperature I'm going to have to deal with? A little bit more air cooled as opposed to being cooled inside or being very, very warm inside the cabinet?
Yeah, that's a good question. I guess the hard and fast answer is anytime you can get more airflow to a transformer, the better off you're going to be. It depends really on the airflow. Are you on the sunny side? Are you on the north shady side? Or is there enough adequate airflow to where you're going? But I think the general principle is, you want to get in hot environments, you want to get as much air to these transformers so that they don't derate.
Yeah, that's a critical part to remember. As that CT gets warmer and warmer, you do have a derated accuracy, which I'm assuming you're about to cover. Sorry.
Yeah, no, that is typically the experience. However, there are some CTs that do not derate. So the GEC Durham Astra extended range transformers, as you'll see our chart here, it does not derate at 85C. It does retain its rating factor. So
Excellent.
This is one of the exceptions to the rules, and a very popular transformer as well. So again, saturation. You put a 400 to 5 transformer into service, and the customer demands 900 amps. Well, your utility is not going to generate much revenue beyond that 800 amps. The CT is going to go into saturation, and the utility is going to lose some money. So, want to make sure you size these accurately. Speaking of which, let's take a look at an 800 amp service, and let's pick a ratio that might work best here for this 800 amps. And again, just a reminder, we want to size according to the rating factor, but we also want to consider the nameplate ratio, because this ideal accuracy range is limited. Okay, so we're going to look at a 3/10 accuracy transformer, and again, at 100% of the nameplate value is where that 3/10 accuracy kicks in. So if we have demand for 800 amps and we put that 800 to 5 transformer into service, it doesn't have much margin in that 3/10 accuracy. You actually be running in the lesser accuracy class for the bulk of the use probably. Now we could put a 400 to 5 ratio in there. It's got a rating factor of 2. So that gets you from 400 amps to 800 amps. That's pretty decent. But if we size by the rating factor and we pick a 200 to 5, we have a much greater range to generate revenue in that ideal accuracy range. So the best selection for this is going to be your 200 to 5 rating factor of 4, 0.5 burden. We'll get into burden here in just a few minutes. For now. So the burden of the secondary circuit is the total resistance of all the components in the secondary circuit. This is the wires, the test switch, the resistance or burden in the meter block, and any other components that are part of that secondary circuit. The burden rating of the CT must be greater than the burden of your secondary circuit. That's important, because if it doesn't, it drives the test point outside of that ideal accuracy class.
It's also reduced secondary current to the meter.
Yes, yep, good point. So again, we want to choose the transformers based on accuracy class. Toss this one in here because, as Jarrett mentioned earlier on that high accuracy transformer, there's going to be ideal environments where you might want to put a 0.15S transformer that goes down much, much lower. Maybe you don't choose a standard transformer. So extended range transformers, this is 3/10 accurate from 40% of the rated current, not the nameplate ratio up through the rating factor. It actually goes down to 40%. Meters lighter loads with greater accuracy. And that 0.6 accuracy starts way down at 4% of the current instead of the 10% of your standard transformer. So by doing that, you're able to cover a much larger range of CTs. You can stock fewer CTs. There's some money savings there. High accuracy. These are our two down here. They're actually two grades, if you will, of high accuracy transformers. You're going to have your 0.15 transformer and then your 0.15S. Okay? Your 0.15 transformer does allow a 0.3 accuracy range down on the low end where these CTs tend to struggle. So, and then your 0.15S allows you one parallelogram, both high and low end of the transformer. It has to perform at 0.15 accurate. So that is what was tested this morning. So here's an example of a high accuracy transformer and how it might replace a number of other transformers. There is a large value associated with this because you can stock one low voltage transformer and cover quite a few or most of your transformers that you're going to use. So you want to choose your instrument transformers by cost, not just by cost out of pocket, but cost back in your pocket. Investing a little bit more in a high accuracy transformer is actually going to save your utility some money. Might cost you a little bit more. Higher burden transformers are more costly as well. So you want to choose the highest burden CT that you can afford. That is the end of our presentation. Garrett, do you have any, or Chris, do you have any other questions?
No, I did want to kind of go over again of kind of my love of the extended range CTs. And the one thing you kind of hit on was the inventory. You can reduce your inventory quite a bit if you had, like this, for example, a 605 CT. We've kind of proven it. That, I was driving this down way below its actual range and still holding its accuracy, which is extremely impressive. Nick is correct that these CTs do cost more, but if you think about it, I've been to a lot of meter shops and I've seen on the shelf, I've seen 200s, 400s, 600, 800s, 1200s, all on their shelf, where you can almost replace it at 1 or 2 CTs just with going with these extended range high accuracy class CTs. So yeah, I'm a big proponent of it, of extended ranges, high accuracy extended ranges, mostly because I'm kind of nerdy that way. I like the characteristics and studying of instrument transformers. I think they're the most fascinating component of the metering system. Meters read what they read, but with transformers, there's so many variables you can move with it, with rating factor, thermal rating, and accuracy class, that I can kind of maximize my investment, let's say, to get the most I need to out of that installation. Sometimes you're going to run across some of these lower end sites. They're not really worth the investment. But if you have, let's say, one of your top 10 customers at your utility, you're going to want to try to maximize that investment. So having the higher class meter, meters nowadays can go up to 0.1. CTs can maximize a 0.15S. So it may be worth that additional investment to ensure you're getting the revenue where you need it.
Yeah, there's a huge value to them, and the word is out. It's been kind of flowing throughout the utility industry the last 5 years that I've worked at Durham for sure, and I think it's only a matter of time until the high accuracy extended range 0.15S transformers really just kind of are really what you buy in your from day to day. So exactly. I think eventually it's going to make all these others kind of obsolete. So, yeah, thanks again for the opportunity. I hope you all guys learned some things. You may have had some questions come to mind. I know I have a question now that is still outstanding from one customer. I'm hunting down an answer for him on that. But if you have any other questions, feel free to reach out to us. Shoot us at Powermetrix an email. They'll get us some questions, and we can follow up and get a clear answer for you.
Yeah, again, I want to thank Nick for joining us and his team. They've been great to work with. And I love my CT, by the way.
All right, yeah. Thank you very much. Everyone have a great day.
Remind everyone, we are not here next week, but we'll be back the following week. So we'll see you then. Probably John Jones will be back. So again, we'll see you then. Thanks, everyone.
Thanks, goodbye.